Hi everyone, thank you for having me. So yeah, before I go on, this is a work that actually is like a sneak peek into a recent VLDB journal paper that we have published about understanding graph data representations in Triplestores. The goal of my talk here is to provide a quick overview of how we can efficiently store a knowledge graph, what are the options about it, and how we can model the space of these options, both about existing techniques and things that have not been tried out maybe, and how to evaluate them, of course. And as I was saying, since this is a big survey paper, here I will go more on the intuition. I will list over a lot of technical details, but I will be happy to discuss them in the questions or offline, of course. And I'm really interested to getting feedback on how this could apply maybe to systems that are beyond Triplestores. As I was saying, here I focus on knowledge graphs. So about many things that we can talk about knowledge graph, I would like us to keep in mind that we are talking about very heterogeneous repositories. Our analysis shows thousands of edge types in Wikidata DBpedia, a lot of different ways to store literal data with annotation of many different types. And of course, the taxonomy is part of the graph itself. So it's not a schema on the side, it's something that is inside the graph, and for this reason also is incomplete and inconsistent, similar to what Angela just discussed about. So of course, when we talk about knowledge graph, in our case, we think about Triplestores that store data as triples. So we have nodes that can be entities, and usually they are identified with IRI. So here in my examples, I will just use this shorthand prefix, but we mean IRI. And of course, there are literals, so many different types, and blank nodes, which are a special kind of nodes that do not have IRI, that are actually understandable outside the graph itself. So we call them Triplestores because we store data in triples that are subject, predicate, objects. And in this case, the predicate is a resource. And this is basically the core of the RDF model. Now, when we want to store a Triplestore, of course, the most naive thing to do is just have a big table with 3 columns, subject, predicate, object, and just store them triples there as a list. We could do something strange and have an hash table in that case, where we have a subject and then the values are the linked list of edge type and object. Of course, maybe instead of just storing a complete list of tables in a list of triples in a random order, we could sort it for some reason, or we could actually use a property table, so a big table where we have 1 row per node, and then we have many columns, 1 for each edge type. Or we could even go in property tables, meaning that we actually split every relationship in an actual relational table with the subject and object. Nonetheless, we have these options, and we have many more options to store triples. And the question, of course, is what's the best for our case of our workload or our data? Well, of course, it depends, and we need to look at how we access this data. So at the core, when we look at querying knowledge graphs, we use a SparkQL. In our case, so we have the triple pattern, which is a triple by itself, where we have variables in place of some subject, object, or predicate. When we combine together multiple triple patterns, we get a basic graph pattern. And importantly, of course, since we are in a graph and we want to query connectivity, we can also use some special kind of triple patterns that have property paths inside. So instead of having a specific edge type, we can decide something, we can specify something that is similar to a regular expression, that then in that case is not a fixed number of hopes, but can be unbounded and traverse different edge types in different order. When we look at how we can execute this, so when we move from the declarative query to something that is more near to the actual physical plan, what we propose is to look at the space of the access pattern to which some different parts of the query can translate to. And in particular, here we propose to look at these features divided into these 5 different categories. One is the constants. So of course, we were saying triple patterns contain variables, but if we look at the constants, those are those that allow us to determine one type of search operation with respect to another. For instance, in one case, we could have here that the node and the predicate are defined. So in this case, we are going to go through the edges of that specific node of that type. Instead, if we put variables in subject and object, and we just specify the triple path, the predicate there, probably we'll be forced to traverse all the possible edges of the type in order to get an answer. Similar reasoning we can do for the traversal, so we can distinguish between traversals that have a fixed number of hops that in that case, for instance, they could be translated to a specific set of joins, maybe, or we could have this path traversal, then in that case would require something like a reachability index for some cases. When we look at filters, as I was saying, that we have an heterogeneous set of data, of course, we could look at range filters. In this case, every literal that is greater than or equal the letter J itself. So if we are looking in alphabetical order for names, but we can specify a specific type of filters. For instance, we want to focus our query only to nodes that are of literal type, or with a specific node type, date, and so on. Then further, when we look at the structure of the graph pattern itself that we are specifying, we can look at the pivot, so how things are connected together. And of course, we could look at binary joins on the same position. In this case, they could be optimized by some materialized view, for instance, or arbitrary n-way joins, for which we have seen the worst case optimal join literally can also exploit specific kind of indexes that ensure that our join has a bounded computation. And of course, what we are going to return is also important for us. So either if we are returning every answer to our pattern, or if you are returning only an information about whether this pattern is satisfied or exists, we may need we may exploit different data representation to answer one or the other. So getting back to our question, what is best? Okay, let's look at a specific query maybe. So in this case, here we have the node and the type defined. So if we look at all the options that I was listing before, we could sort them based on how much operations they required in order for us to get an answer. In particular, here we identify the concept of compatibility between an access pattern and a specific data representation. So we say that an access pattern could be seek compatible if we can retrieve with a single random access the first result of to our access pattern. Sequence compatible if any subsequent random access, any subsequent result can be obtained by only sequence scans. So we just need to look at a nearby position in memory, for instance. And then selection compatible instead tell us whether once we have found the first result, all the subsequent results we will return are actually what we retrieve, all the specific data we retrieve are actually relevant for our query. So we are not going to retrieve pieces of data that we are going to discard later on. If we look at the specific data access that I have here and the different representation that I considered, what we have here is the first design choice. The first design choice, which is subdivision, meaning that we are trying to fragment the data so that we can reduce the number of data itself that we need to retrieve in order to get our answer. For instance, in that case, to have the best subdivision and to make sure that we have a very good compatibility, we could create this different representation where subject and predicate are keys in the hash table, and then we only have the objects as values. Of course, if we change the access pattern or the query, the same data representation could provide us not the same type of compatibility. So in this case, what we can do is actually have one storage representation to answer one type of access pattern and a different storage representation to answer efficiently a different access pattern. So in this case, we have the second design decision, which is across the redundancy dimension. So we are going to add copies of the data in a different organization in order to satisfy a different set of access patterns. And this is what happens in general when we also add indexes to our data. So up to here, we've seen the two dimensions, subdivision and redundancy. There is also a third design choice, which is compression. And in this case, what we are trying to do is to represent data in a way that is compressed so that we can limit the amount of bytes transferred every time we need to compute an answer. And within the compression design decision, there are, of course, the obvious range compression that we can think of, but also replacing, for instance, IRIs or literals with specific IDs is a form of compression. So when we look at all these things together in the paper, we can define this design space, the subdivision redundancy compression design space, and we can identify how moving within this design space can provide us benefit or instead some drawbacks. The idea then is with this analysis that we performed was to provide a extensive and concrete set of access patterns that we need to consider when we try to answer queries for knowledge graphs, and a cost model to evaluate the compatibility of the alternative data representations in order to identify if they are suitable or effective in giving the answers to a specific set of access patterns. Furthermore, what we did, we went through a wide range of existing popular RDF benchmarks, both synthetic and real, and identified the prevalence of these access pattern in those benchmarkings. And to this, we could correlate to recent results or previous results based on what system could perform better. So by looking at the compatibility and the prevalence of the access patterns into the workload that were analyzed. But also what we hope to achieve later on is with this methodology, enable the opportunity to identify an explored solution of storage representations and maybe even automatically suggest different storage representation in order to address an evolving workload. That's all. Thank you very much for your attention, and I will welcome all your questions now.
Thanks, Matteo. Peter has questions or comments.
Thanks, Matteo. Yeah, it's an interesting talk yet and work. Yet I'm getting a bit depressed here, but because yeah, I think that because what I think is the crucial piece of proper storage for RDF, it does not fit in your dimensions, so it's not considered. And that is actually what I was just talking, what also Angela was talking about, which is the structure, the schematic structure of RDF, which is indeed a thing that almost all systems, but not all, but almost all existing systems ignore in RDF. So the fact that there is, in fact, a schema, and I'm not even talking about ontologies here, but about the co-occurrence, let's say, of particular combinations of properties together with each other around the same subject, for instance, or specifically, that makes it possible actually to store or view this data as structured data. And well, actually, it is also possible to then make a system that stores this data in such a structural way, basically as tables, but well, or something of the kind. And that means that you're out of the work of the SP and the O and also all the assumptions that you make about like whether something is random or sequential, they start to be different. So there is like, this is like looking at the moon, but you always see the same side of the moon, but there is also the other side of the moon, the world that could have been. But I hope that at some point it's going to come, because I think that more competent or more performant RDF systems will have to start recognizing this. But this is I'm all ready to. But well, that was a comment. So I think that this is a great start, but there is some dimensions that are not yet covered.
Well, thank you, Peter. I think it's a very interesting opinion, but to be honest, I don't see the problem at all. Meaning that we can, of course, recognize if there are a schema or a redundancy, but this is part of the subdivision or replication dimension, right? So if you identify that some access pattern require often to access some specific properties together, you can have this subdivision, and these are the relational tables in one of the examples that I present, for instance, simplified, of course.
Oh, okay.
When we look about heterogeneity, when we look about schema, yes, it will be very nice if knowledge graph have very defined schema, but that's why I started with heterogeneity, because recently we actually extracted this kind of schema from the Wikipedia and Wikidata, and I can tell you that if you're trying to extract a schema from those today, you end up with hundreds of thousands of recurrent pieces of data, right? And now the question is, should I need to subdivide all of them, or should I keep some of them together, even though they are not the exact same schema, but they are similar, right? So if you look at the schema as we think in the database model, it's not the same kind of schema you have here. But yes, you can have some redundancy and things that are always accessed together. And of course, you can do a subdivision and store them together.
Okay, well, I mean, I'm obviously giving you an opinion without having read your paper that is just out. I just listened to the talk, and I probably completely misunderstand or mischaracterize it. So apologies. But just to give a hint of what I'm alluding to is that in, let's say, in relational data design, like if you design even a data lake or a data warehouse, then some of the choices that you make are, for instance, around partitioning. So how do I partition my tables? And about clustering, potentially. There is lots of work on multidimensional clustering, for instance, of those partitions. The application of things like min-max indexes to do predicate push down and avoid reading lots of data. So this is really the bread and butter of big data processing, and making those choices is what people do who care about managing large scale data. So if we also want to manage large scale graph data or large scale RDF data in this case, then on the surface of it, we don't have even the concepts to think about this. Because if you have a lot of RDF triples, what does it mean to have table partitions or to have clustering of those table partitions? First, you will have to recognize that there is such a thing as a schema. Then you will have to have some kind of physical means of storing data that recognize that schema. And only then can we start talking about, okay, how would we partition our data? Or how would we order those partitions of data? And therefore, until we start doing that, we will always keep looking at the same side of the moon that we already know, and never discover the other side of the moon, the dark side of the moon. Okay.